Hi everybody, my name is Tommaso Cucinotta and I'm from the Real-Time Systems Laboratory of Scuola Superiore Sant'Anna in Pisa, Italy, and I'm presenting you Migrating Custom Bandwidth Servers on Multicores, a work made jointly with my colleague Luca Beni from the same lab. This work has been sponsored by the Ampere European project in the Horizon 2020 framework program. As we know, we are witnessing a relentless growth in computing demand in ICT, which has been satisfied for years by the so-called frequency race, where the frequency of CPUs have been increasing up to the point where we reached the impossibility of handling heat dissipation, as witnessed back in year 2004, when Intel had to cancel their plans for CPU in a frequency ranges between 5 and 10 gigahertz. So since then we've been living in a multi-core race era, and so multi-core and multiprocessing platforms have become pervasive, not only in high-performance computing but also in embedded real-time systems. So noteworthy modern use cases where we need this are high-performance embedded scenarios, like characterized by the need for different type of acceleration technologies like multi-core, GPGPU, and FPGA acceleration, which may be very useful for realizing scenarios as intelligent real-time driving assistance, real-time video processing and object recognition, as well as real-time time series forecasting, which are, by the way, use cases in our in the context of our Ampere European project. We are focusing on open real-time systems where we have dynamic real-time tasks that have to be deployed on multi-core platforms, with the possibility for new real-time tasks to enter the system at any time and running tasks to leave the system at any time. Additionally, we may have requirements of minimizing the energy consumption, which is important especially on mobile devices. In this context, we normally have quite frequent need for migrating real-time tasks among cores. This is often due to the use of utilization-based heuristics for task and core placement. Why? Because, for example, if we use a first fit heuristic, then we have a simple utilization-based overall test that can be based, for example, on the biggest utilization in the system. However, if we consider energy management, whenever we may need to scale frequencies up and down, we have a not so handy situation because we have all tasks packed over the same cores. So we may need to scale up and down frequencies more often than needed, or even when we perform this scale up down, we may need to migrate tasks to restore a first fit environment. If we consider worst fit heuristics, then we have load which is better spread across the available cores, so generally lower response times of the tasks. However, problem is that if we have a new big task arriving, a heavyweight one with a big utilization, then we may have to migrate tasks to make room for this new core. So whatever it takes, we are in a situation where we may need to migrate quite frequently real-time tasks among cores. So the focus of this paper is exactly on these scenarios where we have an adaptive partitioning of real-time tasks on multi-core platforms, where we focus on independent periodic real-time task sets, and these tasks are scheduled by using CBS reservations, so custom bandwidth servers, which, as we know, relies on EDF scheduling. So in this context, each task comes with its own parameters, which are the worst case execution time Ci and the minimum interval period Ti. And each task is associated a reservation in the scheduler, which has a budget Qi of runtime and a reservation period Pi. So normally we set the runtime equals to the worst case execution time of the task, and the reservation period equals to the server period, to the task period. In these conditions, the task would not miss its deadline if the well-known list upper bound for EDF reservations is respected. So the Liouville test saying that the sum of utilization of all reservations admitted on each of the cores has to be lower than or equal to 1. As we know, the CBS handles the current budget, lowercase qi, and the absolute deadline di for each task that is handled by the CBS. So if real-time tasks arrive dynamically at runtime, then we need to have a test that decides whether or not to accept a task on a specific core. So in the scenarios we focus on, we like to use utilization-based tests. If we want to use it, like the one in equation 1, the linear line on test, then of course we can realize the test incrementally, so that we can keep track at runtime of the function vh of t and its variations over time, and so we may use that information to just check easily when a task has to be admitted on the new CPU. Now, the focus of this paper is exactly how do we do this online tracking of VH of T, and how we can use it for admitting new tasks and new reservations. Specifically, we know that when a CBS server is leaving a CPU H, so it can be because of task termination or migration to a different CPU, we cannot immediately subtract the task utilization from the total utilization of the core, because otherwise we risk running the situation shown in the picture, where we have tau1 and tau2 with same parameters. So tau1 is scheduled before tau2 by df. When tau1 terminates, or at this point in the picture, it's migrated or it leaves the CPU. So if we subtract immediately its 0.5 utilization, then we would risk admitting a new task like tau3, as shown in the picture. And it's quite clear that, whatever the parameters of tau3, if tau3 has a deadline which is earlier than the earlier deadline of tau1 and tau2, then basically tau2 will miss its own deadline. So this, in order for not allowing this to happen, we need to postpone the subtraction of UI from the VH of T to a later moment, which can be safely done either at the current deadline of the task, so on the DI of T, or we can even do it earlier at the zero lag time of the task. And this is all well known. A scheduler should track the zero lag times of tasks in order to handle properly this subtraction of UI from VH of T. And for example, deadline scheduler in the Linux kernel has the inactive timer that can be used conveniently for this purpose. Now, when the CBS leaves the CPU, so if we decrease immediately UI from VH, we get an incorrect behavior with the risk of deadline misses. If we postpone subtraction to the zero lag time, then this is safe, but we show in this paper that this is also pessimistic. So actually we can improve on this by keeping the simplicity of utilization-based admission tests as they are generally known, by refining how exactly we perform admission, considering basically the still active utilization of tasks that recently left the CPU. So let's get to the details. So if we consider at each time t the sum of all still active utilizations of migrated reservations in the future, then this can be individually be modeled as a step function that keeps remembering step function VIHM of t that keeps remembering the utilization UI of task tau I in time till the time delta I, which is the zero lag time for the task. And beyond that point, the function goes to zero flat. If we sum up all these functions, we obtain still a step function, VHM of t for the core H, of the active migrated utilizations of all tasks that migrated from the CPU. Now, from a practical standpoint, we don't need to remember all the history of the system. This function can conveniently be remembering only the tasks that recently left the CPU, and once we reach the current time, which is the delta I of some of these tasks, we can actually forget about the task entirely. Fundamentally, this function can be stored from a practical standpoint as a set of pairs where we have the utilization of a task that left the CPU along with the absolute time delta I that the zero lag time of that task had when the task left the CPU. Okay, so a new task, in order to admit a new task with the utilization UI in the system, the known utilization test checks that the utilization of currently hosted tasks on the CPU plus the utilization still active from migrated tasks that recently left the CPU plus the new task utilization doesn't violate the least upper bound limit 1. This can be rewritten also this way, and also ultimately we can turn around the utilization constraint into a budget constraint. So we can say, okay, this already well-known test states that we can accept a new task if its budget is lower than or equal than its period multiplied by this, the leftover bandwidth at the moment. This can be visualized as in figure 3 in the paper, as basically if we consider time t when we want to admit our new task, which has period reservation, period pi. So this will be admitted if its budget is lower than or equal than the Qmax, which is the area of this rectangle in the picture. We propose a different budget test, where an extended one, less pessimistic one, where we admit a new task if its runtime is lower than or equal than the area of all this area in the curve, which is contained within the VH plus VHM T curve and the step function and the least upper bound limit N1. As it's visible, it's clearly the new limit includes the old one, so it's a less pessimistic test. The proof, in order to prove this, we have to consider first a lemma, which we call lemma 6.1 in the paper, where we have a task set with a schedule which is schedulable on a core H, and we consider a task tau I that is activated sometime t. So at that moment, the deadline of this task will be the I of t. We basically state in this lemma that we can move the release time of this job. We can remove it earlier to a time t prime that is lower than t, and this doesn't really break schedulability of the task set. So this can be shown as follows. So if we consider the original schedule of the task set, we call it sigma. So it can be seen as a function that gives us the task ID of the task to schedule on the CPU H at any time t. Then we have the original schedule obtained if tau I is released at time t. Then we have the sigma prime is the new schedule obtained when we anticipate the release of tau I at time t prime. As the deadline of tau I is unchanged, then it has the same dynamic priority in sigma and sigma prime. So tau I cannot really miss its deadline because of anticipating its release time. Actually, tau I will have even just more chance to run, if any, and so it won't be in a position to miss deadline because of this anticipation. So the problem, the verification has to be made on other tasks. Can we be sure that anticipating release of tau I will not break schedulability of others? To this purpose, we consider T0, which is the time after which all jobs are active in the interval t prime t, and with the earlier deadline than the I of t completed. So if this T0 falls after t, then there's no problem at all. So all tasks are basically having a deadline earlier than the I, so basically changing the release time of tau I will not affect anything, and sigma will be equal to sigma prime. If T0 is lower than t instead, as shown in this picture, then we might have a third task, a tau j task, which has a deadline greater than the I of t, as shown here in the picture, and this task might have been delayed in the time window going from t prime to t, actually from t0 to t. So a deadline miss can only happen for such a task having a deadline that is beyond the deadline of the task tau I, which is the task we anticipated the release of. Now the reasoning here is very simple. So as in the original schedule sigma, tau I was scheduled without any problems. So basically it has a guaranteed budget qi within its deadline di of t. So if we consider any time window in which after t0 we might have scheduled task tau I for a certain time, for example q0, we call it q0. So we prefer to schedule tau I instead of any other task tau j with deadline beyond tau I of t, of course, because it's an EDF schedule. Then in this case, this anticipation of the schedule of tau I would have basically left a hole in the schedule, so would have left a corresponding time window here of the same duration q0, in which tau I certainly will not run, and this time window occurs before the original tau I deadline the tau I deadline di of t. So in this time window of duration q0, we would actually be able to let tau j recover the delay, and this happens all before the I, which is also before the tau j on deadline. Now this reasoning can be extended. I mean, this is only if tau I impacts tau j directly. If we can consider also indirect impact, these details are in the paper. However, so the overall point is that anticipating the release time of a task in the schedule will not really change anything from the viewpoint of schedulability. Now, we consider the proof of the whole theorem by composing and applying this lemma in a number of ways, so in a specific way. So at the time t, we need to admit a new reservation, which we call qn plus 1 pn plus 1. For each migrated utilization ui scheduled to be subtracted from the core migrated utilization sometime delta I, we can imagine that a new task of utilization ui can safely enter the CPU at that time, at delta I. So all of these new tasks that may enter the system, so which have the delta I between the current time and current time plus the p and plus 1 in the future, okay, they can all be given the same absolute deadline, exactly equal to t plus p and plus 1. So now we are in a situation in which we already know that we can safely schedule all these little tasks released at times delta in the future. However, due to lemma 6.1 actually, we know that we can move the release time of all these little tasks to an earlier time. Specifically, we can move it back to time t. And doing that, we have a situation in which at time t, we are releasing a number of tasks with same deadline, which can be, which is perfectly equivalent to releasing a single task with the sum of all the budgets and sum of all the budgets and the same deadline. So this way we obtain the proof of the theorem, so that the maximum budget that can be admitted is actually equal to the one visually depicted as this area in the picture. We made some experimental validation of this theorem by simulation. So we use the RTSim real-time system simulator, which can perform simulations of a number of different task sets, number of different conditions, different tasks with single core, multi-core platforms, different schedulers. So we use the random task sets generators by Ambersons by generating task sets with an overall total utilization of 0, 90, 95, and 99 with number of tasks from 4 to 10, and periods with a log uniform distribution in 1000 and 2000 within this range of time units, with a period granularity of 100 time units. We created a scenario where we started the task sets synchronously. Then we pause the simulation at random times until we found a moment in which at least k tasks had a zero-like time in the future. And this was done with k equals to 1, 2, or 3. Then k of said tasks were killed, and the new task was added to the CPU with a random period having the minimum between the minimum and twice the maximum among the times of the deadlines of the k killed tasks. And also the runtime of this new task was set equal to the maximum allowed by theorem 1. Then we continued the simulation for a duration equal to 10 times the biggest period in the task set. And finally, we verified that we had no deadline misses in this period of time. So as well known, it would have been sufficient to keep running the task sets till the maximum period. As you know, after that, nothing really changes. So we logged also the maximum runtime obtained according to the old utilization-based test of equation 7, the bandwidth gain defined as the Q new minus Q old relatively to Q old. So it's the additional bandwidth we could actually, the additional budget we could give the task relatively to the one that we would have originally granted it with the original simple utilization-based test. The obtained results are shown in this figure 7 in the paper. So we have the experimental CDF cumulative distribution functions of the response times of all the tasks in the simulation, and we have verified that under all the configurations parameters, the maximum achieved response time is within the period, so it doesn't go beyond the period. And also we have measured the bandwidth gain, and here in the table we report the average bandwidth gain that we obtain with this technique. It goes from, for example, 2 in some cases to 35 in other particular cases. However, remember that in these scenarios we have chosen the scenario in a way that was useful to highlight the advantage of the technique. In conclusions, we proposed a novel utilization test for admitting CBS reservations to a CPU, which is less pessimistic than existing tests. Same ease of use, but the same ease of use is useful in scenarios with frequent migrations of real-time tasks among CPUs, for example with adaptive partitioning, and on mobile platforms when applying the VFS changes to CPU frequencies. And we demonstrated correctness of the test formally and verified it by simulations. Future work, we would like to integrate this within SCAD-Deadline, both for regular multi-core platforms, so SMPs, and also for power-aware variant of SCAD-Deadline that we are engineering on big later and dynamic ARM architectures. And we would like to check the applicability of this in the context of the Ampere-U project use case scenarios in the automotive and tramway industries. This is a set of our recent related publications, and thanks for your attention.